Good afternoon. These are going to be your notes for 16.2, modeling exponential growth and decay. Okay, so in here, when you use the formula, y is the final amount, a stands for the original amount, r is the rate of growth or decay, and t is going to stand for time. Okay, there are two different formulas, one for growth, one for decay. So exponential growth is y equals a times 1 plus r to the t, and decay is y equals a minus 1, or a times 1 minus r to the t. Okay, so the example on the left says the population of a city is increasing. Okay, this should let you know that this is growth. At a rate of 4%, which that tells us that r equals 0.04 each year. In 2000, there were 236,000 people, so that's going to be A. In the city, write an exponential growth function to model this situation, and then find the population in 2009. So this gives us time, which is going to be 9, because it went from 2000 to 2009. Okay, so they just substituted everything. Make sure when you write these functions that you write them to the t. Okay, you can't fill the number in initially. Okay, the other one says the population of a city is decreasing, which would be decay, at a rate of 6%. So this tells you that r 0.06, I didn't write that very well, each year. In 2000, there were 35,000 people in the city. So I kind of wrote over that. 35,000 is going to be our A. Write an exponential decay, and then find the population in 2012. So because it went from 2000 to 2012, our t is going to be 12 that time. So the model would be y equals 35,000 times 0.94 to the t. And that is because we had to do 1 minus 0.06. Okay, so we're going to look at 1, 2, and 3 at the bottom here. And it says write an exponential growth function to model each situation, and then find the value of the function after the given amount of time. So it says annual sales at a company are 372,000 and increasing, so this is going to be growth, at a rate of 5% per year, and then 8 years. So it would be y equals 372,000 times 1 plus 0.05 to the t. So if I write, and I don't need to see this necessarily, you can skip this step if you can. So it's y equals 372,000 times 1.05 to the t would be the growth function for that situation. And then you can just plug it into your calculator, and the answer after 8 years would be $549,000, $613, sorry, dollars and 43 cents. To do the exponent on your calculator, remember it's the little caret button, the up arrow on the right hand side of it. Let me see. Grab a calculator real fast. So it's that button right there above the division. Okay, number 2 says the population of a town is 4,200 and increasing at a rate of 3% per year. Find 7 years. So our initial amount would be 4,200. And our rate is 0.03 to the t. Again, you don't have to write that. You can just do y equals 4,200 times 1.03 to the t. Okay, and then you would plug in 7 for t, and you get 5,165 people. Okay, the last one says write an exponential decay function. So its monthly car sales for a certain type of car are 350,000 and are decreasing at a rate of 3% per month. Find the 6 months. So y equals, this is going to be the 350,000 times 1, and this is plus, this is decay, so this is actually subtract 0.03 to the t. So this would be y equals 350,000 times 0.97 to the t. So when you plug the 6 in, you would get $291,540.20. Okay. A couple more notes on the other side. So you're going to graph on a calculator and state domain, range, end behavior, and the asymptote. And number 1 is f of x equals 300 times 1.16 to the x. Okay, remember to graph, you need to hit the y equals button. And then you just type in 300, begin parenthesis, 1.16, end parenthesis, and then you're going to use the caret button I showed you a minute ago, and then X. When you go to graph this, they're not going to fit in a normal window, so you're going to hit zoom, and then 0, which is fit, and it will begin to graph. Okay, the domain, because it goes on forever both ways, left and right, we write the domain bracket x, it's just a long line, it would be negative infinity is less than x is less than infinity, end bracket. Zoom in a little bit. The range when we take a look at our graph, the y doesn't go below 0. So we're going to list that as y, and that long line again. Y is greater than 0. End bracket. The end behavior, we did this the other day. Remember, we list the right end and then the left end. So looking at the graph again, you would say as x approaches infinity, y approaches infinity. Okay, again, because as we're going further to the right, the graph is going up, so they're both positive. The left end behaviors as x approaches negative infinity, y is approaching 0. And so the further the graph goes to the left, the closer that graph is getting to 0. And then the asymptote it would be y equals 0. Remember, that is the line that the graph approaches but never actually crosses. Okay. Second one is f of x equals 500 times 0.8 to the x. This one's going to be decay because it's less than 1. So we hit the y equals, and you can just clear that out. Do 500 parenthesis 0.8 end parenthesis to the x. And again, you're going to use zoom 0. Okay. So our domain, again, it goes on forever. So it would be bracket x negative infinity is less than x is less than infinity. The domain, again, you can see it doesn't dip below 0. So just y is greater than 0. The end behaviors on the right end as x approaches infinity, y approaches 0, so we're getting closer to the y-axis or the x-axis, and the left end behavior as x approaches negative infinity, y is actually going up, so that's going to approach infinity. The asymptote for this one, again, is y equals 0. So if you missed today and you're having to do this, you'll have to come in to use the calculators, or maybe you can Google a graphing calculator, but it would have to be a graphing. The homework for tonight is 16.2, page 594 to 595, number 2 to 20 even. Okay, have a great afternoon.